Great. So our next talk is from my co-founder, Yehonatan, and he's going to introduce some of the exciting research we've been doing at dWallet Labs. So, Yehonatan, thanks.
Okay. My mic on or no? Yeah? Okay, so I'm super excited to be here. Especially the lineup is incredible, so I'm happy and excited, privileged to speak next to all these amazing cryptographers. Today I'm going to talk about 2PC-MPC, which is a research that we did in dWallet Labs. We attempted to solve a problem that is at the heart of interoperability and security of Web3. And for that, we needed to actually do some breakthroughs in the normal cryptography theory behind it. All right, so let's start. So I'm Yehonatan. I did my Math BSc during the high school, so I finished at the age of 19. Later, I served 5 years in Matzov, which is Israel's national cryptography and cybersecurity unit. I was in the cybersecurity side. I was doing like low-level kernel, embedded systems kind of things. But we have people like Delevar, VP Research, Vichai that was in the unit with me on the more cryptographic side. Later, I was doing some hacking. I did Android kernel hacking for about 3 years, and I got to do it remotely, so I traveled the world while doing that, and it was fucking incredible. And I got to the next stage, which was I wanted to come back, do some startup. Took me some time, but after a year, we came up with this idea kind of independently, and then later we merged. So now we're doing this, dWallet Labs. I'm not going to talk about this. Let's just talk about what we're going to do today. It's not going to be a very use case kind of presentation. I'm going to talk about cryptography mostly. And I'm going to talk about the problems that we have to solve first. And later, I'm going to talk about how we solve them and the actual stats and optimizations that we can do. And I'm going to tease you about what we're going to do in the future or what we want to do in the future. So our basic problem is to decentralize ECDSA signatures. And that I'm not sure that it even signifies something when I'm saying that, but let's talk about what were our problems when we talk about decentralizing ECDSA signatures. So the first one is it's a tricky one. It's not the obvious one when you think about this problem. It's actually the maintenance problem. So the maintenance problem is about how do you manage and store keys when you have a permissionless network that hosts decentralized wallets. So if you have a bridge and you have a few like vaults, so you have like just a few keys, I think you can manage storing them independently, where each validator has a key shares and they just hold the key shares. But if you have a permissionless network whose objective is to onboard most of the wallets in Web3 now and in the future to use this infrastructure as their security backend. So you're going to have millions and millions of wallets to deal with. And that could be very hard to maintain. And it's even harder when you think about it being a permissionless network in which the validators change. So you have parties changing in every epoch. And you need to have not only the keys available, but actually usable. And that's going to be hard. I'm going to speak about that very soon. Some problems that I care about, but I don't know if other people care about. Communication in almost all threshold ECDSA, or actually all practical threshold ECDSA signature schemes before 2PC-MPC, was P2P communications. Whereas theoretically, a blockchain only allows for a broadcast channel. So I would want a broadcast-based protocol. Now, scalability, throughput, latency was just not even close to what we needed. If we want thousands of parties computing thousands of transactions per second, whereas the state-of-the-art identifiable protocol was doing maybe 20 parties in maybe minutes for a transaction, for a single transaction, then we were very far off from where we needed to be. And lastly, I think, is this idea of involving the user. So we want this to be a completely non-custodial wallet. And for that, we need the user to be cryptographically required for the process of generating signatures. And when we want to do that, we call this, first of all, non-collusiveness. So that's this idea of the network cannot collude and actually steal assets. And when we do this, we actually want the user to not be burdened by the size of the network. As I said, it's going to be a permissionless network. We want it to be as big as possible, so security be as big as possible and as decentralized as possible. But we want the user to not experience that. So this idea of locality means user is O of 1. It's constant in both communication and computation. And we want to achieve all of that while keeping identifiability. So let's start with the maintenance problem, because that was actually quite surprisingly the first problem we tried to solve. At first, we were kind of optimistic. We saw, it's a T out of N protocol when you look at the CGGMP, and we thought, so actually you can just plug in whatever T and N you want. It turned out not to be that way, but we found that out rather late. In any case, we started from the maintenance problem. The maintenance problem, for me, is hard because if you have this network that holds various keys, right, and each validator needs to keep key share for every one of those keys, then the amount of key shares that every validator needs to keep private is O of M, where M is the number of keys. Now, what happens when we have some kind of validator change? Then we need to do a reshare. This is a cryptographic operation in which you keep the same private key. So if you go to the previous slide, you'll see that the keys remain the same in the orange. But what happens is the key shares that every validator holds, they will change. So that the sum will still be the same, the sharing is still the same, but the actual shares are different. And this is an expensive operation. It takes at least O of N or O of N squared for every key. So you'd have an operation that is dependent both on the number of keys and in the number of wallets that you need to do in every epoch, which could be as little as 24 hours. That is completely infeasible. Now, what happens if we involve the user? Now, if we involve the user, then actually we would need the user to be involved in this operation as well. So if you have 1 million users, 1 million keys, and you need every 24 hours each of the users to be active, unless if they don't do it, they lose access to their wallet. That's not possible. The solution we came up with was to use a threshold additively homomorphic encryption scheme in such a way that the actual key, the private information that the validator holds, is a decryption key. It's not the signing key. And we use this property where for AHEs, the encryption scheme is homomorphic. So you can have two messages, you sum them up in the encryption of them, and you get the encrypted of the sum. And we use that in order to actually have just one threshold decryption key shared. That's the one in orange in the middle. You have every validator have just one share, this one share. And then we save the signing keys, or at least the network share of the signing keys, encrypted under this key in the state. So now we have many dWallets. We have one key that every validator needs to change. And better even, one key that they need to reshare. So on the DKG of CGGMP that we started by wanting to adopt, every party also sent their encryption of their share, right? And then you sum them all up, because the encryption is homomorphic, you can do that. and you get just a single encryption of the network side of the signing key of the ECDSA signature. Then in Sign, you could apply threshold encryption over the signing key plus some random nonce R, and you would reach a sharing of the private key, and you could use that for signing. So now we have as many wallets as you want in the state. We don't need to maintain each and every one of them. We don't need to save backups. We don't need to refresh each and every one of them independently. And we can change the validator sets as we wish, while still just maintaining this one decryption key. And the actual security of each and every one of the signing keys, the access structure is derived from the access structure of the decryption. We had another problem. There were no practical threshold AHE schemes at the time. After that, there were works. I think most notably is one work about threshold class groups. So this is an assumption that I'm not sure everyone wants to take because it's not as research as standard. But that was also published after we did our work. But we wanted to use a standard one. So we worked on Tiresias, which is a large scale, it's maliciously secure threshold palier. And we managed to do pretty scalable things. So we managed to do decryptions in under a second. So that's your sub-second latency for the decryption, with up to 1,000 parties. And with Tiresias, we can actually adapt to solve the maintenance problem of CGMP, but we still have the scalability problems. We still have the communication problems because CGMP was P2P based. But we did manage to adapt CGMP to solve non-collusiveness, and we didn't solve locality. So that was the point in which we thought, OK, great success? No. It's not great success because it's not scalable enough. And we want something that could actually be the infrastructure for custody in Web3. And for that, we need something that will be much more scalable. And we asked the question, can we use Tiresias, which has the promise of being this scalable, because we show that we can do decryptions under a second with up to 1,000 parties. And I'm wanting to ask, can we use that to do a threshold ECDSA protocol? There was a work by GGN that was published in 2016 that actually did threshold ECDSA based on threshold additively homomorphic encryptions. I didn't mention it before, but I'm talking about additively homomorphic encryptions, where Zvika was talking about fully homomorphic encryptions. Additively homomorphic encryptions are a weaker, simpler building block, and we show that you can use that. Of course, you could use FHEs for what I'm speaking about, but that could be costly, right? And this work by GGN16, it was even before the first practical threshold ECDSA work that was published by Lindell in 2017. And Lindell's was 2PC, and this one is multi-party. So you ask the question, why is it not famous? And the answer was there was no threshold AHE at the time that was practical, and they relied on trusted dealers. But we'll get there. Let's just have a look about how the protocol goes through, because we are basing ourselves on this protocol, and we extend it. So the DKG, the distributed key generation for this protocol, is kind of like our adaptation to CGMP. So you take every party samples key share, and they broadcast the encryption under the threshold decryption key of this key share. And you sum all up, because it's homomorphic, you get the encryption of the key. And a small recap about an ECDSA signature. It's actually based on kind of two secret things. And you have the key, and you have the nonce. And the thing about ECDSA is that you have an inverted nonce, which is a problem with MPC. But The signature, you don't need to remember this formula, is just based on these two public things, which is the generator G and the message M, and these two secret things, which is X and K, the key and the nonce. And the easy part is to reach, there's two parts in the signature. You have R equals K inverse times G, and you have S tag, which is also includes the key. The easy part is to reach K times G. That is because K times G is actually a homomorphism also. So what you can do is each party can just sample their nonce share, and they publish their nonce share times G, so that's Ki times G. And you can sum everything up to get K times G. That's very easy. By the way, the idea is that you cannot reach from K times G to K because of the discrete log assumption, so you can broadcast all of these things. The tricky part, of course, is multiplication and inversion. In MPC, that's always the tricky part in these kind of schemes. But we show that using threshold AHEs, you can do that quite easily. So how do you multiply the secrets? First of all, you take an encryption of one of the secrets. And then what you do is you multiply that secret by a scalar, because you are the party with the secret. You can multiply that locally. And what you get is you get an encryption of your secret share by the total secret. So you have E of X, which is the whole secret key. And you take your nonce share, you multiply that locally. You get an encryption of the secret times the nonce share. And this you can broadcast because it's encrypted. And you can sum it all up because it's homomorphic. And you get an encryption of the nonce by the secret key. And how do you invert in MPC? You use a mask. So you sample a single, use random mask in symmetric encryptions. They call it one-time pads. And you encrypt this. You multiply this, right? So if you multiply this, you get an encryption of a masked nonce, right? You get gamma, which is the mask, and K, which is the nonce. And because it's masked, you can actually decrypt that. And now you have this in plain. Because it's in plain, you can think of it as a scalar, and you can do local operations with that. So you can reveal that, and you can invert that. Inverting gamma times K is like having the multiplication of the inverted gamma and K. And you multiply that by the encryption of gamma, which is the mask, and you reach the encryption of the inverted nonce. So there was a little bit of mathematics here that was not super important if you didn't get it. But the idea is that using threshold AHEs, we can reach all of these factors, the inverted nonce, the secret key, and the message, and the random, and R, which is the first part of the signature. And you can build an encrypted signature from that. And now comes the only threshold decryption part that you need. OK, in GGN16 you needed two, but for us, I'll show you later how you can do it just with one decryption. And then you just decrypt the signature, and you get the signature, right? OK, this was the semi-honest variant of GGN16. Malicious security requires actually using zero-knowledge proofs to actually show that every step along the way follows the honest protocol. That was the problem with GGN16, which was they didn't really have these zero-knowledge proofs that were practical. They required using safe primes, which is just impossible to generate in MPC unless you want to kind of wait the lifetime of the universe. But you could do it if you're willing to trust some dealer. We are not willing to trust some dealer because we are trying to do a decentralized solution. So we had to come up with these zero-knowledge proofs to fix this. Let's do a small recap about zero-knowledge proofs. So this is completely independent of what I talked before. So if you lost me along the way, please come back. The simplest zero-knowledge proof is Schnorr's knowledge of discrete log. what you want to do is actually you have this x times g, right? That's a public, you can think about it like a public key. For ECDSA, that's a public key. And you want to show that you know the witness, x. If I send you x times g, you don't know, it just looks like a random kind of point. You don't know what it is. And I want to prove you that I know what the secret is. So the protocol looks kind of like this. The prover can sample some randomizer, k, and they send you the public value of that k times j. And the verifier can sample some challenge. The prover can do some formula that is a combination of the randomizer and its witness. And the verifier can actually verify that you had to know x in order to do this. And using kind of a generalization of Schnorr, we designed a novel, batchable, aggregatable, zero-knowledge proof system that enables malicious security for GGN16, so no trusted dealer is required. But our proof system is an enhanced version of this. It's enhanced, first of all, it's an enhanced version of Maurer proof, which is a generalization of Schnorr proofs that works for any homomorphism, because Schnorr was just for this knowledge of discrete log. So you have any homomorphism phi in which you can plug in two numbers, a and a tag, and you can sum them up under phi. And Schnorr is just one where phi of x is x times g. And Maurer proofs are a generalization of Schnorr proofs. They work kind of the same thing. They just use the homomorphism as the formula instead of the hard-coded x times j. And we use enhanced Maurer proofs, which add range claims to the language. And that's the novelty that we have, is that we wanted to add range claims to the language. So it's no longer a strict homomorphism because of these range claims. But why do you need them? First of all, encryption schemes like Palier are working in a different group than the elliptic curve group that you're going to do the signature. So we want to work over the integers. Now, thankfully, Palier encryption works in a much, much bigger group than the ECDSA group, so you have some space to play around with. But you need to prove that you never went through modulation so that you actually are emulating working over the integers. And for that, you need range claims. You also need range claims if you want to work with RLWE-based encryptions, like Zvika described before. That is because the noise needs to be small. So you need to actually prove the noise is small. If you don't do that, you might leak the key. So how does this work? There's a very simple trick in enhanced Maurer proofs, is that we are using a range proof and a Maurer proof, and we add to the Maurer language the commitment over the message for which we use the actual language that we want to wrap with another range claims. So there's some code here, but you can see that the witness space group element for us, the witness of this language, the enhanced language, is always going to be composed of a message of a commitment scheme, a randomness of a commitment scheme, and some unbounded witness that you can use for a language. And it always maps onto the statement, which is the commitment of the commitment scheme, and the statement of the language that you want to wrap by adding range claims. And the idea here is this commitment scheme, this commitment is going to match the range proof commitment over which you are proving the range. And the homomorphism is pretty simple. You can take this message of the commitment space, and you just transform this by composing the message of the range proof onto the witness of the language. So if you'd think about it, I'll show you soon, but if you'd think about it that you have some range proof that you don't know how it works internally, In the end, it just proves range claims on a lot of numbers. If you could take these numbers and using some formula, transform that into, for example, the witness X, which is the secret key for the ECDSA signature, then you can show that using this witness, later you do the homomorphism of the inner language, and you show that it's the same witness that was proven range claims on. I won't go into much more details here, but basically from this you compose the language witness, from that you compose the language statement, and you add the language statement to the range proof commitment over the same message, and this is enhanced malware proofs. So you have a proof that's compounded by a malware proof and a range proof, and you verify both of them, and the trick is you verify both of them on the same statement, the same commitment. So then you have this parity where you show that they're linked. There is some other trick that I'm not going to describe, that you need to kind of verify that the response of the malware proof does not go through some kind of range, does not go over this range. But I'm not going to describe it, but that's just more of a mathematical trick you needed to add. And using these enhanced malware proofs, we can actually remove the trusted dealer assumptions. So let's give one short example of this kind of language, is that you have this encryption of discrete log language in which you want to say, here is X, this is my witness, and I want to give you an encryption of this witness and a public key that corresponds to this witness, and I want to show you that it's the same witness used for both. So you know X times G, you know E of X, and you want to know that they match, right? This is the encryption of discrete language. And now the idea is that we want to make it more complicated by saying that X is actually a part of this elliptic group. So you have Q, the order of the group, and you want X to be smaller than that and bigger than 0. So that's your range claim. The encryption of discrete log language just takes the plaintext space of the encryption, so that's a message, and the randomness, and it maps onto the ciphertext and the group element, right? The encryption and G times X. I'm not going to go into this. But using all of these building blocks, we actually managed to transform GGN16 using TerryCSR threshold Palier and using enhanced malware proofs into a 3-round protocol that actually is broadcast only. It's identifiable. It's large scale. So what's left to solve? I'm sorry, we had a lot of problems. So we solved maintenance, right? We solved it early on. Now everything is broadcast-based because of the encryption scheme, which makes all the message public. All the messages are public, and we have zero knowledge proof, so it's identifiable. It's scalable because our encryption scheme, our threshold encryption scheme, is scalable. And what's left for me to show is actually we can reach this non-collusiveness and locality features that's by the access structure of 2PC-MPC. So that's what I want to talk about next. And the throughput and latency I'll leave for later on. If we want the user to be required for an MPC operation, we want the network to never be able to perform a signature without the user. How can we do that? The very naive solution is to have the user be the same number of players like the network is, right? If you have 100 players in the network, so you're going to say the user is 100 players, it's going to keep 100 secrets, and it's going to do 100 operations in every signing operation. That's very, very expensive, right? Like, that's infeasible. Especially when you think about like the network is going to be like a lot of like very computationally high servers, and the user is just like a web browser. So what we introduced is this notion of 2PC-MPC. This notion, I think, is beautiful because you have the network emulates in MPC a two-party player. So if you have a two-party protocol that does ECDSA, one of the parties is going to be a decentralized network with thousands of validators. But the other party is just going to be a user with a web browser, and he doesn't know how big the network is. He doesn't know anything. He just thinks he's talking to one person. Lindell 17, as I said before, is one very good 2PC protocol for ECDSA. And it's relatively simple. I'm not going to describe it now. But what I'm going to say is that there you have, if we're going to take P2, the second player, and we want to distribute that, we see we have two secrets, right? The nonce share, and we have the secret key share. And we want to distribute them. Now, I think if you distribute them, but all the messages of the protocol are still going to be the same, then you have the witness X, the secret key of the ECDSA signature, being X1 plus X2. So the user is going to be required in every signature, right? Because the other party just can't do it without it. And the user still receives one message every time and one proof every time. So if we can get that, it still has locality. And it still has non-collusiveness. And how can we imagine doing such a thing? Well, I think it could be imaginable that we do the same tricks that we did before to do a multi-party signature in order to do all of the computations, right? Because they all involve like multiplying and inverting things in MPC. We already know how to do that, right? I think the harder problem is how do you prove one proof over all of these things that you did in MPC, and it still corresponds to the statements that you want to prove. And for that, we use proof aggregation. So Maurer proofs are linear. As you see, you have K plus CA. There's no multiplication. It's very easy to aggregate them in multi-party computations. And therefore, Maurer proofs are aggregatable. And then if your range proof is aggregatable, and hence Maurer proofs are aggregatable, I'm not going to describe how exactly they're aggregatable. But the idea is that if you take an aggregatable proof scheme and you use proof aggregation in every place that every party used to send a proof, you can have a two-party computation emulated by a multi-party party. And that could actually solve both non-collusiveness and locality. And it does solve that. OK, lastly, let's talk about performance. I think that public protocols are pretty cool. Now, why I think that? Because there's a lot of optimizations and tricks you can do that you couldn't have done with unicast-based protocols. And I want to say that our protocol is practically O of 1, which should pose some, like, really, on your side. But yeah, let's say why. Well, the thing is, if all the messages are public, then all of the O of n computation is over public values. So you would think that maybe we have some kind of way to amortize this. And we do. The first thing that you could do is to amortize the threshold decryption. Now, I remember that I was very much obsessed with this problem. Like this was the biggest bottleneck in our protocol, right? You had to do threshold decryption over n messages. In Palier, we use Shamir secret over the integers so that actually the secrets themselves are O of n. And then it makes it so much expensive. And I was very annoyed because I said every one of these players needs to do the exact same thing over the exact same values, get the same result, and they do it for no good reason. And I remember being in like this rock show, and I was thinking about this problem instead of dancing, or while I was dancing. And, and I was like, wait, but the encryption of Palier is deterministic once you know the randomness. And the randomness is not secret once you decrypt. So what if during the threshold decryption, we also recover the randomness, and then you have not only the message, but only also the randomness. So you take this encryption of M with randomness R, and you give to all the other parties both M and R, and then these other parties just need to encrypt M using R and see that it corresponds to the ciphertext that this party they don't trust said they decrypt. So apparently someone thought about it before, and there was a paper describing this. And this was a really cool idea, but it had its problem. First of all, it's just for Palier. It doesn't work for RWE schemes, for example, because the randomness or the noise needs to be kept somewhat private. Otherwise, you might leak the private key. And it adds communication rounds. Now, I'm going to talk about a different story. We have some friends here from that actually were the authors, or part of the authors of DKLS. And I attended the lecture of DKLS in Singapore with Dolev and Avishai. And I remember that they talk about this trick about how to reduce the round complexity. And they have this trick of how to form the signature of ECDSA in such a way. And actually, we thought about it. We walked down the moisty, beautiful jungles of Singapore, and we were obsessed about this problem. Can we make a free-round protocol? Can we make a free-round protocol? And what we turned out to find out is that we could. And the big thing about it is that now, instead of having 2 threshold decryption rounds, like in GGN16, you have just 1. And when you have just 1, it means you're decrypting a signature. And what's cool about the signature is verifiable. And that does not depend at all about the encryption scheme. So now we have a scheme that is completely generic in using every threshold homomorphic encryption scheme that is also amortized, because in the last stage, the very last round, you decrypt a signature, and then just one person decrypts, all the others verify it, and you have amortized O of 1. So that's the first thing. The second thing is that the proof aggregation, although it's asymptotically O of 1, it does much more lightweight operations. Because the idea is, instead of doing n exponentiation when you do verification, so every verification is a very high complexity operation, or at least in computation it's very high weight, you do multiplications, or if you think about, I was talking additive notation before, so you have additions instead of multiplications. And actually it turns out to be a big deal, because the base rate difference in computation is very high. It's orders of magnitude cheaper to do additions than multiplications. Depending on the group, it can be between 100x to 1000x improvement. So if you have 100 parties, you're practically O of 1. And that's the basic idea. And it can be shown in these graphs. The left one is for verification. The right one is for proof. And the dotted one is if you do have aggregation, and the straight lines are if you don't have aggregation. So obviously, if you do have aggregation, verification is constant because you verify one proof. And obviously, if you don't have proof aggregation, it's linear because you have to verify each of the proofs of every party. You're not going to get it for free. You're going to pay in proof. And the proof time, when you have verification, when you have aggregation, does increase linearly. But you see that the graph does not increase linearly from the get-go. It has this kind of curve where it takes a little bit of time to catch up before you actually feel the linearity. And that's why we say it's practically O of 1, because up to a certain number of parties, which is actually a pretty big number of parties, you feel like it's a constant operation. And now let's get to really asymptotically amortized O of 1. All this that I was just describing is completely public. Our protocol is publicly verifiable. You can take all of the public steps, push it, shove it into a snark, and then all the other parties just verify a snark, which is constant. Now, I don't want to do that actually in practice, because the snarks constant is going to be more expensive than everything I described before. But the idea is that actually you can get to asymptotically O of 1 using this trick, which is kind of naive, so naive that Dolev didn't want to put it in the paper even. But I thought it's cool to point it out. Some statistics. So I think that the idea here is that we are getting to even 1,000 parties, and we can manage to do that, right? We can manage to do that in seconds. Also in pre-signature, you can look this up later. But the idea here is that this is before parallelization, and you get a complete signature in 100 players by, I think, a few seconds. And 1,000 players, you get it like 100 seconds. If you parallelize it over 100 CPUs, you can get it in a second. So we got kind of to where we wanted. What's my conclusion? Well, first of all, public protocols are cool, right? Like you couldn't do all of these tricks before. And with Tiresias and 2PC-MPC, like we actually show that malicious security, it can be achieved for free, and I'll show that very soon. But the idea is that 2PC-MPC solves all of our problems. Okay, not really, but almost all of our problems. So theoretically, it solves all of our problems. Practically, we have a problem with the range proof. I'll talk about it just now. But it solves definitely the maintenance problem. The communication is completely broadcast. It reaches thousands of parties. It's non-collusive. It's local. It's identifiable. It's actually even publicly verifiable, which I didn't even know what it means before we achieved it. But we have throughput and latency problems a little bit. Why? Let's talk about it soon. But the idea is that using all of this, we can actually imagine a massively decentralized network that offers non-collusive signing mechanisms. And this is going to be dWallet network. And dWallet network is going to, we want it to be, the infrastructure for access to all Web3. And you can use it for various interoperability, custody, onboarding solutions. And that's the basic idea. We are going to have in dWallet networks smart contracts from other networks that are going to dictate the logic to when the validators are going to sign. So you're going to be able to control signatures from any network that you want, like actually Ethereum mainnet, or Sui, or Aptos, or any other chain that you would like. What's our future work? Is to solve these two small problems, not that small. But let's show why I'm very optimistic, and I say that 2PC-MPC actually solved all our problems. The reason is this is a logarithmic scale, and we show what takes the most in computation in our protocol. And the green is bulletproof, as you can see, because it's a logarithmic scale. It's not like we do this after this after this. Like the green is all of this. So bulletproofs is by far the most expensive thing in our protocol. Bulletproof is the range proof that we used. And without that, if we think that we don't have bulletproof, malicious security is free because malware proofs, we call it Schnorr here, is completely, you don't even see it here. And here is still negligible next to the statement computation. So if we don't have range proofs, we get malicious security for free. And I think we showed this with Tiresias before, and we showed this with 2PC-MPC now. And I want to claim that you want to go there, you want to aim there whenever you are doing a practical MPC protocol in real life. You want malicious security for free, and I think you can get it most of the time for free. So we need a new aggregator range proof. That's my future work. I would say a caveat here that if you use class group-based encryptions, which is a different assumption that I don't trust as much as I trust Palier, so we chose not to use it. But if you use it, then you don't have range proofs. You don't have range proofs. You don't have bulletproofs. You only have compute statements. That was going to be your bottleneck. And the idea is that right now, we can have all of the problems solved if we trust class group encryptions, because the compute statement phase is very, very fast. The bottleneck in statement computation is the encryption. And Palier encryption, for example, takes 20, 30 milliseconds. You have a few of those, maybe 3 or 4 in the protocol. So you can have sub-second MPC operations right now for free if you don't have the range proofs. But we do want to use Palier, so that's our next mission. We're working on it. We have some permission needs, but let's see. And that's it. I just want to say thank you. It was really I enjoyed talking here. And all of this is open source. It's released. The paper is out. The code is out. We are in testnet. You can look it up. And that's it.